Today we'll be talking about our profile builder or PC software, which accompanies our LIBS model instruments. The great thing about this software is it turns our normal portable elemental analyzer into a powerful scientific desktop instrument. Basically, with LIBS, you're able to take it into the field and get in situ results, but when you combine it with this PC software, you gain the functionality of a normal benchtop high-end instrument. The first thing we'll be showing here in the software is how you can quickly take a test with the software and easily do some spectral analysis. LIBS spectra are packed full of information, so LIBS spectra are packed full of information, so it's useful to have a desktop screen to be able to kind of move around the spectrum and identify peaks and really get into the details of the data. So I'll take a quick test here and I'll show you what kind of cool things you can do with Profile Builder. So I've got a sample in front of the instrument's nose. I just hit the scan button and you may be able to hear the laser firing in the background. The test is finished and we're just transferring the spectral data over to the PC. And now we have our spectrum. So once we have a spectrum, it's easy to go and zoom in. We can look at different peaks. We can kind of zoom around the spectrum and look at various things. Say we wanted to know if a specific element is showing up in our spectrum. We have a menu option here to show emission lines. And from here we can go and choose any element in the periodic table to view the lines. So right now I've got magnesium selected, and we can see on the spectral plot it's showing us where the strong magnesium lines should be showing up in our spectrum. The height of these lines should also signify the relative intensity of each of the peaks in the spectrum. Look around, we can do this with any element we want. So let's look at carbon, for example. Here we can see the two nice strong carbon peaks, the strongest one here at 193. Not a whole lot of carbon in this sample. And then there's a second one up here at 247, which we do not see. Let's take a look at one more element. Let's try palladium. I know this sample has a bit of palladium in there. So we've got the palladium emission lines showing. If we go and zoom in on the strongest lines, we can start to see there's a peak here. It looks like this palladium line might have another peak on its shoulder, but there's palladium, there's another small palladium peak there, and we can shift over to the right a little bit, and there's another palladium peak on a shoulder. So as you can see, LIBS spectra can have many peaks involved, so it's nice to have an easy to use spectral analysis software like this to be able to really understand and analyze a spectrum. We talked about if you know a specific element that you want to look for in your spectrum, you can use our LIBS lines library to identify where the peaks should show up and then go look for those peaks. Another way to do this would be, we have a spectrum, we want to know what's in it, by going to this Analyze menu, and we'll hit Analyze Spectrum. What this does is it actually searches the entire spectrum and will find peaks based on the different peaks that it finds. It's going to search through our LIBS line library and identify the elements it's confident are in the spectrum. So that's what we see down here in the bottom. We have a list of elements that have been detected. This works a lot like our companion software Element Pro, which is actually run on the instrument in the Android operating system. But here we can see detected zirconium, so we can click on zirconium. It'll quickly show us all the zirconium peaks, and we can go and confirm, all right, there we go. Those are our zirconium peaks. We see 5 in a row, and that's a great way to confirm that zirconium actually is in our sample. We have magnesium, calcium, barium, two different ways to approach analyzing a spectrum. Let me turn off the emission lines and we can move around and look at some other spectra. Another great feature of this software is to select multiple spectra so you can overlay, so you can see for sure what the differences are within a group of spectra. Here it's obvious these group of peaks we were just looking at for zirconium are quite different for each of these three different samples. So this is just another nice tool you can easily view and identify the spectral differences between one sample to the next. Today we're talking about the Profile Builder PC software that goes along with the SCIAPS LIBS instruments. The great thing about Profile Builder is it takes the portable instrument that we know as LIBS handheld, and it helps to convert it into a scientific laboratory grade analysis tool. I'm going to redo that.
Sure.
The great thing about Profile Builder, when combined with our LIBS handheld, is it turns an instrument that can be carried out into the field into a powerful laboratory grade scientific instrument. Basically, you can use the instrument as a portable device, connect it to your computer, and then it really expands the kinds of things you can do with it. We use Profile Builder for building calibrations, analyzing spectra, overlaying spectra, doing some fancy spectral analysis techniques, and spectral processing. This is the introductory screen to Profile Builder. You can see we have different calibration types or different modes we can log into. In this case, we're going to use empirical mode, meaning we're going to build our own calibration. But there's also alloy, which is designed specifically for alloy analysis. And then there's also geochem for geochemical analysis in mining or environmental. Down here we choose our connection technique. We have the option to plug in an IP address. So if we wanted to work wirelessly through Wi-Fi, we could plug in an IP address there, or we can connect through USB. In this case, we'll connect through USB. Down here we have factory mode, which we can disable. Now we will connect with this button. The instrument is now passing all of its calibration data over the PC, and you're able to see this data getting transferred, and soon we'll be able to start building a calibration from scratch. So right now we're in empirical mode, and SCIAPS has developed a nice calibration wizard to help the user step through the process of building a calibration. So I'm going to go to Cal Wizard, and I'm going to open this up. The first step when creating a calibration would be to name your calibration. So in this case, we're going to be looking at some car catalyst samples that have some low levels of platinum, palladium, rhodium, and there are a few other elements that might be interesting to look at as well. So I'm going to name this calibration catalyst. I'll hit next, and this will take us to step 2. Step 2 is where you teach the instrument the calibration standards you're going to be using. In this case, I have 4 calibration standards. Ideally, we'd have even more standards, but you can get by with 3 or 4 if you have to. So I'm going to insert standard. I'm going to insert 4 standards. The first one is A, second is B, then C, and D. These are our calibration standard names. And now I'm going to insert the elements. So this will allow me to find the elements I want to measure with this calibration. So the first few we're going to look at are platinum, palladium, and rhodium. These are common elements in car catalysts that people are trying to measure. I'm also going to add magnesium. In this case, our customer wanted to see magnesium as well. And then cerium is another interesting element that we can try to build a calibration for. When I've selected all the elements, I'll hit done. And now I can plug in the concentrations of these different elements. I can switch the units from percentage to ppm, and platinum, we have 1882 parts per million in sample A. Sample B has 1981 parts per million. Sample C has 427 parts per million, and sample D has 1356 parts per million. So now I can go through and fill in the rest of these. So I'll do palladium as well with 550. Sample B will have 589 parts per million palladium, and I'll just continue filling out the rest of these elements. Okay, so I've finished entering in all of the concentrations for our calibration standards. Now I can hit next. From this screen we can select a calibration standard, hit the scan button, and start collecting our calibration spectra. At step 4, we'll hit save. So now that we've created our calibration, we've defined our calibration standards and their concentrations, and we've also collected spectra for each of those samples. So we actually shot each sample 3 times to build our calibration with. Now the last step is building our intensity ratios. We use intensity ratios with libs because it helps to have a reference line somewhere in the spectrum to normalize your intensities to. So in this case, the first part of our ratio will be adding the numerator. So the top part of our ratio for our magnesium calibration curve is going to be a magnesium peak. So one of the main features of Profile Builder is what we call the Cal Wizard, which allows a user to step through the various steps needed to build a calibration from scratch. Cal Wizard lives up here in the top menu and helps to step you through each part of the process when building a calibration. This first part is naming the calibration model. Today we'll be looking at some car catalyst samples that have low levels of platinum, palladium, and rhodium. And so I'm going to name this calibration catalyst. We'll go to our next step, and at this point we need to define our calibration standards. We have 4 standards in this calibration, so it's a pretty basic setup. Ideally we'd have a few more standards to work with, but to keep this example simple, we'll deal with four samples. I'm going to add 4 new standards, and I'm going to name the standards A, B, C, and D. And now I'm going to add the elements that we want to measure with our calibration. So we'll look at platinum, palladium, rhodium. In this case, we're also interested in magnesium and cerium. So here's a few elements. We'll hit done when we're done selecting. And now we can enter our assays for these different calibration standards. Up here we can change from percentage to ppm for our units. I'm going to change to ppm and start entering the assays. So I finished entering all my assays into the calibration standards screen. I can hit next, and from this screen, this is the acquire data screen. So I can select a standard and hit scan, and I will collect the spectral data for that standard. Typically you want to test each standard multiple times, so in this round I'll do 3 tests each. We'll skip through that part for now, and I'll just hit next. And finally, you just need to save the calibration, so I'll hit save. So now that I've built the calibration, I'm going to go to my empirical calibrations drop-down menu and choose my new calibration called Catalyst. This shows you we have different elements defined for the calibration. We have 4 standards that we've tested. We've tested each standard 3 times. And over here, this is where we would see our calibration curve. The final step before we can view our curve is defining our intensity ratios. That's done down here in this box. We use intensity ratios in libs because it's very helpful to ratio the element you want to measure to some sort of reference element. In most cases, you're referencing or ratioing to an element that is sort of the base material or represents the balance of the elements or the bulk of the material. So in this case, these are catalyst types of samples. We have platinum, palladium, rhodium, cerium, and magnesium that we want to measure, but there's also a significant amount of silicon in these samples. 20-30% or more silicon that is relatively stable across all 4 calibration standards. So in this case, I'm going to try to use silicon as our reference line or our ratio element. For magnesium, I'm going to click in here to our intensity ratio, and in the top part of the ratio we want to have a magnesium peak. When we hit the plus sign, we come to this menu which suggests some possible magnesium peaks that we can try using. So you can click through. Here's a magnesium peak at 279.6 nanometers, and then we can kind of scroll through and look through at each one of these different magnesium peaks and quickly judge which peaks look nice and which maybe wouldn't make a very good calibration. So I'm going to jump to this 280.3. This is a common magnesium line that's pretty strong, and I'm going to hit create. So we've got magnesium in our top part of our ratio. Now I'm going to hit the plus sign in the bottom part of our ratio, and I'm going to go find silicon. Let's look. Here's a 288, which is a strong peak. So now once I've finished my ratio, I have the element we want to measure on the top, and we have our reference element on the bottom. You can see we now have a curve filled out. So it's instantly gone through our test spectra, integrated the intensity of our magnesium peak and divided it by the intensity of our silicon peak, and you end up with a calibration curve. So we're looking at our intensity ratio on the x-axis plotted against the concentration of magnesium in our standards on the y-axis. So in this case, we've got 4 samples. They all trend pretty well together with this second order polynomial. If we wanted to try to look at a linear fit, we could do that over here in our curve settings. We'll leave it at 2 for now. We can also force it through 0 if we want. And on top of that, we can go and try to tweak our regions even more. So here's our magnesium peak. The green part in this spectrum is showing us the region that we're looking at when we integrate the peak. So if we wanted to, say, make that wider, we could see how that affects the curve. As we get kind of further away from that magnesium peak, you might see that the curve doesn't look as good. So ideally, we want to be kind of capturing that peak perfectly in the middle of our region. Make this a little wider too on this side if we wanted to. And it's nice because you can get the instant feedback of how you change the width of your region and how that in turn affects your calibration curve. And we could do the same for the silicon region as well. So in this case, I've actually gone through and I've made some calibration curves for the other elements in this set of samples. We've got our rhodium curve. These samples have rhodium up at about 225 ppm and lower. We've got palladium. Here is our palladium calibration curve. And cerium. If we want to go look at the cerium peak here, we can see there's cerium. Here's silicon as our reference line again. And then finally platinum. Here's our calibration curve for platinum. So that's it. That's how easy it is to make a brand new calibration from scratch using the Profile Builder SCIAPS PC software.